So the last thing we'd like to talk about when we talk about Laplace transforms is the problem of feedback, and how to use feedback in continuous time systems in order to stabilize unstable systems. So we'll have two little presentations about this. So we'd like to be able to find the transfer function of a system when we include a feedback system, and then try out different control policies to create new transfer functions, hopefully some of which are going to be stable. So this will make a bit more sense after we sort of set up the problem. So the problem is the following. You have a system G, which we'll call a plant. That term comes from chemical engineering, which is where this stuff was originally developed. You have an input signal x of t with Laplace transform x of s, and y of t with Laplace transform y of s. And you have this plant G, and the problem is this is unstable. And why is that? Because the ROC does not contain the imaginary axis for this G. And if we think of G as being a causal system, which is usually a good assumption in control systems, that means we have a pole in the right half plane, right? So a simple example is just having a pole at s equals a, right? And a is positive, so a is greater than 0. So what we'd like to do is somehow design something around this plant. This plant might be, an actual system that we built to achieve a certain task, or more often it's a system that is sort of handed to us. Like, here's this robot arm. Now figure out a controller for this robot arm. And because we're handed this system and it's unstable, we want to be able to use something to try and stabilize the system to make sure that we create a new transfer function between x and y, which is stable. And we can do that using feedback control. So how does that work? Well, what we do is we take the output y of s and we just feed it back into a feedback system f of s, and we multiply this f of s, this output of f of s by -1, or we subtract it from x of s. So this is negative feedback. And hopefully this negative feedback will cause this system to be stabilized. And why do we put the minus sign there and not put it into f of s? Well, just convention, really. And also the idea is that you think about positive feedback, not obviously in terms of like you're getting positive feedback on your performance in the class or something, but like positive feedback like a feedback loop. Positive feedback like in a microphone creates the instability, and I'm sure you've maybe encountered this if you have two Zoom sessions going on two different devices. Like if I had Zoom on my tablet and on a laptop going at the same time, then the microphones interacting with each other will cause a positive feedback loop and cause this high frequency saturation of the speaker. So similarly, so in that case, then positive feedback is considered a kind of bad thing, and this negative feedback is useful for control because it emphasizes the fact that you're kind of subtracting something from the input x to get the output, to get the new input to the plant G. So that's just a little bit of philosophy. We call this G of s, if we kind of ignored the rest of the feedback system here, we call this the open loop system because there's no feedback loop. And then what we want to do in feedback system design is design this feedback system f of s to close the loop. So we're closing the loop on this thing in order to control the system. So we want to find the overall transfer function for this closed loop system. That's the name of the game, and this is just a little trick of algebra, and I think once you see it once or twice, it becomes a little bit clearer. So I recommend also kind of going through these derivations that we have here on your own, or rather, on a piece of paper, so that you understand what's going on. So what do I mean by that? Is that we have this block diagram here, right? And so let me call this thing, say, r of s, this signal here, right? So what we actually have is that r of s is equal to f of s times y of s, right? Because it's y of s going through f of s, and convolution in times multiplication in the Laplace domain. And then what we have is that y of s is equal to, now we have over here, this is going to be x of s minus r of s, right? So, and y of s is equal to g of s, and let's call this, v of s. So this is g of s times v of s, and v of s is equal to x of s minus r of s. Right, so if I kind of didn't want to write these intermediate signals, we can sort of say, well, the output of f of s is f of s times y of s, that's r of s, and the input to g of s is x of s minus r of s minus f of s y of s. So we just write this out. Y of s is equal to g of s, it's the input to g of s, times this g of s times this input, and then you just do a little bit of algebra, and in the end you get out this sort of formula for the transfer function. So the new transfer function is our old transfer function g of s divided by 1 plus f of s times g of s. And this explains how feedback can help, because in general the poles of this system are going to be different from the poles of g of s, and we hope that we can kind of move the poles of g of s over into the left half plane so that we can stabilize the system. So this relation is sometimes known as Black's formula. That is, the new transfer function is g of s over 1 plus f of s times g of s. And what it shows is that negative feedback control, it shows how it changes the negative feedback control changes the transfer function of the original system, the plant, g of s, in the open loop configuration to this closed loop transfer function, h of s, that we just derived. So let's do a little bit of a quick example before turning to some other examples. So let's take g of s just to be 1 over s. This is an integrator, so this, remember, is unstable. And then we're just going to use f of s equals to 1. So remember, we have our picture, so we're going to have 1 over s. We're going to have a minus sign here. And we're going to just, we're in fact just going to, f of s is just going to be a passive connection back. So there's no, it's just a wire. Here's y of s, and here's x of s. Right, so we've essentially taken a wire from the output y of s and made a gain of -1 on it, and then stuck it back into an adder with x of s. Algebraically, what's happening? We have this g of s is 1 over s, f of s times g of s is 1 over s. We just multiply top and bottom by s, and we get this thing, which is stable. Right, because the pole is at s equals -1. So this closed loop system is actually stable. We took this integrator, just wrapped a wire around, and basically stabilized the integrator. So that's pretty cool. So can we do this for more complicated systems than just the integrator? That's the real question. So does the same trick work, say, if I have a pole at, so this is a pole at s equals a, where in a, remember, we're thinking of a as being greater than 0. So let's again look at the simple case, f of s is equal to 1. So again, we're looking at this picture. X of s goes in. Here's g of s. So this is 1 over s minus a. Then we're just going to wrap this back around, and here's y of s, right? So this is our system. So applying the formula, we have g of s, and we have g of s times f of s over here. F of s is just equal to 1, so that's the same as g of s. Multiply top and bottom by s minus a, and we get 1 over s minus a plus 1. So this will be stable as long as a is less than 1. So that's a little disappointing, because, it means that we can't just connect the wire back. But maybe we can do better if we allow the wire to have a bit of a gain. So we'll take this wire and we'll put a gain, k, on it. And so now we have this feedback k. So then we have a new transfer function. H of s is equal to 1 over s minus a. That's again our g of s. And this is g of s times f of s. and then we just cross multiply by top and bottom by s minus a, and we get 1 over s minus a plus k, right? And this is just a redundant version of that. So this is stable now if we choose k greater than a. So again, now we don't have a condition on a, we have a condition on our feedback gain k. And this case where I choose the feedback to equal to some constant is called proportional control, because the feedback signal is just proportional to the output signal. So we can see there'll be other types of feedback control where we take functions of the output signal, and we'll describe those in a minute. So what does this say? This says that as long as we are allowed to put a sufficiently large gain k on our feedback signal, we can use negative feedback to stabilize a single pole, unstable pole system. That's all we need to do is wrap a wire back with an amplifier on it. Okay, so what does that leave us with if we have something more complicated? So here's another example of proportional control. Let's try this same control, f of s equals k, on the following plant. Here we have a pole at -5 and a pole at +2. So that's an unstable system, right? So this thing makes it unstable. And so we can just apply the same Black's formula, cross multiply, and then we multiply top and bottom, and we get this following expression: 1 over s squared plus 3s minus 10 plus k. So as long as we choose k greater than 10, we can make the system stable since all the poles will be in the right half plane. So as a hint, to see this, you can just look at the quadratic formula and sort of see where you start getting complex roots, for example, with negative real part. Right? As long as the real part is negative, we're in good shape. The system has been stabilized. So this looks like it's good, but this actually is maybe not so good, because this system, we require an amplifier, a gain of 10. So that, if y of t is very big, then a gain of 10 means that it's even bigger. So like if y of t is a high voltage signal, then this feedback signal is going to be an even higher voltage signal, and becomes a question of whether you can actually implement this kind of proportional control in the first place. So there's actually 3 forms of control that people often use for feedback systems in the simple case, and it goes by PID control. So P is proportional. So we have a control signal which is just proportional to the output signal. Then we have something which involves the derivative of the output signal. Remember, s is multiplication by s is taking a derivative, so that's called derivative control. Then we can also look at integral control, where I take the integral of the output signal and feed that back instead. So in general, you can have all three. You have PID control, but oftentimes you can get away with just using 2 of them, so PD control or PI control. I'm not really sure about ID control. I don't think I've ever seen an example where ID control is what really fixes things. But the implementation of these feedback strategies, of course, involves being able to build circuits or systems which can do the integration or differentiation. And sometimes one type of operation is easier than the other, which means that you're limited to, PD control or PI control. So let's look at the same plant that we had before and look at PD control. So here we're going to have f of s is equal to a proportional part plus a derivative part, so kp plus kd times s. Plugging that into our Black's formula here, we can see when we cross multiply by this denominator that we're going to get a 3s is going to be, this kds is going to get added to this 3s, and then we have this kp minus 10 in the constant term. So here you still need kp greater than 10 because you need to get rid of that negative 10. Negative 10 has to be made positive. But the poles of the stabilized system have moved left because this s term is a bit larger. So again, you can take a look at the quadratic formula and see why that's true. It comes from the minus b term. And so the resulting system is more stable because the poles are farther. So why is that? The poles, what do I mean by more stable? The poles are farther left, right? And we can move them. We can with KD greater than 0, right? So we can move the poles farther left to make that happen. So to try things out yourself, you can try using proportional and proportional derivative control to stabilize these open loop systems. The first is unstable system, which is actually a good model for a motor. You can see that if you look at the book by Fawaz and Ulabi in the chapter on applications of the Laplace transform. Then you have, then we can try it for a system with more complicated, which has 3 poles, 2 of which are unstable. So this might mean that you need something a little bit more, with a little more oomph than just proportional control, or maybe not. You have to take a look. And then finally, here's an example of a system which actually, I think, cannot be stabilized with proportional or proportional derivative control. And I guess try to verify that, or maybe prove me wrong if that's not the case. And each of these should be hopefully give you a chance to apply Black's formula and get a sense of how these things work yourself in a more hands-on way.